Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 19th video lecture. And today we want to conclude chapter, I think it's chapter 6, and move on back really to chapter 3. So today we're going to cover something about curves, which is an important part of complex analysis when we look at curves in R2. Which we can associate R2 to the complex plane. And we're also going to move on back to chapter 3 to look at series, and we'll start that during this lecture. Okay, so as a definition, for this last topic, a continuous mapping gamma of an interval a to b into Rk is called a curve in Rk, or we call it a curve on A to B. And I'll do examples in a few seconds. But first I want to talk about two types of curves. So the next definition is that if a curve gamma is 1-to-1, then gamma is called an arc And another definition, if gamma is a curve such that gamma of A equals to gamma of B, then gamma is called a closed curve. I'd like to look at two examples. So if we define gamma equaling to, let's say, x and x squared, then gamma, we could say, maps 0 to 2 into R2, and we can think of R2 as like our complex plane. And pictorially, here's what we get. So gamma is taking 0 to 2 into this type of picture. So the first coordinate in R2, the x value, is just equal to x in 0 to 2. Okay? So the y value, though in R2, the y value in R2 looks like x squared. So what we get is, we get the same points as if we were graphing y equal to x squared in the xy plane. That is 0, 0. When x is 0, we get 0, 0. And then put back 0. And then put back 1.
we get out 1, 1, and when the input value is 2, we get out 2, 4. And it looks like our usual curve. Another example is if we let gamma be equal to, let's say, cosine of x and sine of x, then, again, gamma will map, let's say, something like 0 to 2 pi into R2. And pictorially, here's what it looks like. What gamma is doing is it's taking 0 to 2 pi and it's yielding out this type of picture. So think about when x is 0, we have 1, and sine of 0 is 0, so we get the point 1, 0. So that's this point. 1, 0. And then as we continue to let values of x run through 0 to 2 pi, what you get is this picture. You get this unit circle. Okay? So that's what the picture would look like. This first picture is an example of a curve. It's also an arc because it's 1 to 1. Here, this is a closed curve. Example of closed curve. Okay. Here's a definition. Associated to each partition, let's call it script P equal to x of 0, x of 1, all the way up to x of n of A to B. And to each curve, gamma on A to B is a number, lambda, I'm calling it capital lambda, of, it depends on the partition and the curve, and it's equal to the sum, as I run from 1 to n, of the norm here. So a lot of times I use double bars. Okay? It's the norm. But I'll use single bars. Here's what it's going to be. It's going to be gamma of x of I minus gamma of x of I minus 1. Which we will call the sum of the distances between output values of gamma for the partition P. And what we're going to work towards is trying to get the length of the curve. And so this is our definition for the length of the curve, in some sense, with respect to the partition that's given to us. Essentially, what we're thinking, in our previous example, for instance, if we partition up 0 to 2, okay, break it up, and then you look at, for those breakups, let's say we partition it to here in this example, let's say our partition is 0, 1, and 2. That's all. And what you do is you take the distance between these 2 points and the distance between these 2 points, and those distances between those points is going to be the sum of the distances. The sum of the distance is going to be the sum of the distances of our gamma. Well, it's gamma. Of course, that was with respect to a given partition. And so, here's a definition. It says the length of gamma, which we consider a curve on A to B, okay, is, we denote it big lambda of just gamma, okay, and it's given by, is the sup over all partitions of lambda of P of gamma. Another definition is that if this length, lambda of gamma, is finite, is less than infinity, then we say gamma is rectifiable. It's a rectifiable curve. Okay, here's the last theorem that we're going to do in this chapter, having to do with integration. It says, if gamma prime is continuous on A to B, then gamma is rectifiable and its length equals to the integral of the norm of gamma prime. And we're going to prove this theorem. Okay, we're going to show an inequality in both directions between these two numbers. That's how we're going to prove that they're equal. That is, we're going to prove that this length is less than or equal to this integral, and that this integral is less than or equal to this length. And so, here's the first part. If we consider some number, x sub I minus 1, some two numbers, x sub I minus 1, which is less than x sub I, which is less than or equal to b. So we're thinking of these as two partition points, if you will. Then, by the fundamental theorem of calculus, and this is part 2, what we end up getting is that this norm, this is norm, not absolute value, gamma of x sub I minus gamma of x sub I minus 1, that's going to be equal to, it's going to be the norm of the absolute value from x sub I minus 1 up to x sub I, okay, of gamma prime of, if you will, t, some dummy variable, dt. And by the result that we did last time, we can say that's going to be less than or equal to. That's going to be less than or equal to the integral from x of I minus 1 up to x of I of the norm of gamma prime of t dt. So, if we think of this lambda with respect to p and gamma, so this length of gamma with respect to this partition, if you will, that's going to be equal to the sum, as I runs from 1 to n, of gamma of x of I minus gamma of x of I minus 1 here. That's norm, okay? Which is going to be less than or equal to the sum of these types. I'm running from 1 to n, these intervals. Integral from x of I minus 1 of x of I of gamma prime t dt. But that, if you sum up over all the partition values, that's nothing more than the integral from a to b of the norm of gamma prime of t dt. And so, and this is true for any partition of a to b. Look, this part, this equality, is that, look, if you split up a to b into a partition, x of I minus 1 up to x of I, you might remember, if you only integrate from a to b, you can integrate from a to c and then from c to b. It's the same. Okay? It's integrable. And so here, we're integrating it over a bunch of those partitions, if you will, breaking up not only from a to c and then from c to b, but to a bunch of partition points. But it's still, the fact will hold true and allow us to say that these two things are equal. So this tells us is that the length of gamma, okay, which equals to the sup over all these partitions of these lengths with respect to these partitions of gamma, that's going to be less than or equal to the integral from a to b of gamma prime of t dt. This was a bound for each one of the partitions. So it's a sup, it's an upper bound for the set of all these lambda of p gammas. So the sup of it is going to be definitely less than that, less than or equal. So that's one of the parts of the inequality that we're looking to show. And now we work on the other part, which is longer. So if we let epsilon be greater than 0 be given, since gamma prime is continuous, on a to b, then that tells us that gamma prime is uniformly continuous. So, we've been given this epsilon, so there exists a delta greater than 0 such that the norm, which represents the metric here, the norm between gamma of s and gamma prime of s and gamma prime of t, that guy will be less than epsilon, and that's true for all s, right here, for all s and t element of A to B, well, such that, or with, that's part, the norm, this is norm, but really it's absolute value this time, between S and T is less than delta. So that's absolute value, that's norm. So what we do is we let script P be a partition of A to B with the delta xi being less than delta. And that's true for all I. So consider any Ci such that x of I minus 1 is less than Ci, could be less than, which is less than or equal to x of I. Then, because of the delta x of I being less than delta, then t minus x of I will also be less than delta. And so what we get then is that the norm of gamma prime of t minus gamma prime of x of I, that will be less than epsilon because of the uniform continuousness. Now what that implies, and these are norms, but you can work with it a little bit, and that will apply. There's a little bit of steps here skipped here. But that implies then that gamma, the norm of gamma prime of t, so it's derivative, that will be less than epsilon plus the norm of gamma prime of x of I. Thus, we have that the integral from x of I minus 1 to x of I of the norm of gamma prime of t dt, that's going to be less than or equal to, replacing this with something bigger, x of I minus 1 up to x of I of the norm of gamma prime of x of I plus epsilon dt. Okay. And this is a constant with respect to t. So this is equal to the norm of gamma prime of x of I times delta x of I, this distance, and then plus epsilon times that norm, I'm sorry, not norm, but that distance, delta x of I. This is a norm But this is a number, and you can bring this number inside the norm because it's positive, and what you get is that this yields at the interval, the absolute value, I should say, or the norm, I should say, of this interval, x sub I minus 1 up to x sub I. This is norm, okay, of gamma prime of x sub I dt. Okay. This is the same thing, plus epsilon times the delta x sub I. So this quantity is the same thing as this quantity because I move this inside. I'm able to move that inside. But that's equal to, so here we have the norm as x sub I minus 1 up to x sub I of, well, gamma prime of t. So I'm going to introduce gamma prime of t. Plus gamma prime of x sub I, that guy's already there, minus gamma prime of t. So I've added gamma prime of t and subtracted it. dt in its norm plus epsilon times delta x sub I. And that can be rewritten as the norm of the interval from x sub I minus 1 to x sub I, gamma prime of t, of dt, plus the norm from x sub I minus 1 to x sub I of gamma prime of x sub I minus gamma prime of t, okay, dt, and then that is the norm plus epsilon times the delta x sub I is still there. Now, using the triangle inequality, we get that this is less than or equal to the norm of the first interval plus the norm of the second interval plus is epsilon delta x sub I. Now, by the fundamental theorem of calculus, R2 again, this quantity is the equal to, well, I guess, yeah, I say equal to. This is going to be the norm of gamma x sub I minus gamma of x sub I minus 1, okay, plus, well, I'm going to change this to be less than or equal to. And what I'm going to do is move my norms inside the integral, which makes what I'm about to write be bigger than the norm of the integral. So the integral of the norm got big. Okay? And then we've still got this plus epsilon times delta x sub I sitting here. Okay, that in turn is going to be less than or equal to this first norm, so gamma of x sub I minus gamma of x sub I minus 1. And then plus, and what I'm going to replace what we're integrating by, I should say. So I had x sub I minus 1 of x sub I, and I had the norm between the difference between gamma prime of x sub I and gamma prime of t. But that norm is going to be less than epsilon because of the partition that we're picking and the continuity of the gamma prime. So this is less than epsilon dt, and then plus epsilon times delta x sub I. Well, that part right here is equal to itself. Okay. And here we're integrating a constant, so this is really epsilon and then this distance between this x sub I. So I have two of them, 2 times the distance between x sub I. That's what I got. Let's put it normal here. Let's put that delta. Okay, so the integral from a to b of the norm of gamma prime of t dt, which will be equal to, well, it would be the integral from x sub 0 to x sub 1 of this norm, plus the integral from x sub 1 to x sub 2 of this norm, this function, plus all the way up to plus the integral from, if you will, x sub n minus 1 up to b of this function. That will be less than or equal to the sum. So as I run from 1 to n, for each one of these quantities here, I can replace it by what's written right here, which is going to be gamma of x sub I, it's normal, it's minus gamma of x sub I minus 1 plus 2 times epsilon delta xi, which we can break that into its own sum as well. Okay, so I just mentioned I can make this into 2 sums. So I will equal the sum as I run from 1 to n of the gamma. It was x sub I minus gamma of x sub I minus 1 plus the sum as I run from 1 to n of 2 epsilon delta x sub I. But that's equal to, this part right here is nothing more than the lambda of gamma with respect to the partition that we made, plus 2 times epsilon times b minus a. This sum of these change in the x sub i's would just be b minus a, where I'm factoring out the 2 times epsilon. That's a constant, pull it out, and then if you just sum up those distances, you get b minus a. And that is going to be less than or equal to lambda of gamma, the length of gamma, plus 2 times epsilon b minus a. So since epsilon greater than 0 is arbitrary, then what we have is that the integral from a to b of the absolute, or the norm of gamma of t dt, that is going to be less than or equal to this length of gamma. So we have both inequalities. We were looking. And so as a conclusionary statement, since, for the first part of the proof, that the integral from a to b of gamma prime t dt is less than or equal to lambda of gamma. I think that was the last thing I should say. And for the first part, lambda of gamma is going to be less than or equal to the integral from a to b gamma prime t. That's what we initially showed in this proof. Then they have to be the same. And that is the proof. Okay, what I want to do is do a little bit of work from chapter 3 about series. And so let me start here. So this is part of chapter 3 we haven't done before, and I'm looking at numerical series. We had concluded what we wanted to do out of chapter 6. And we have looked at chapter 3 before, but not this part of it. And so let me just start off in our work here, unless otherwise stated. What we're going to be working with, we're going to assume what we're working with is a sequence. The sequences. We'll say A sub n is a sequence of complex numbers. I'm working with complex numbers, okay? Sequences of complex numbers. And what I want to do is get up some definitions here. So, given a complex sequence, A sub n, then A sub n converges to A. We had talked about in chapter 3 about the convergence of a sequence in metric spaces, but I'm going to write down this definition specific to complex sequences, which we really are recalling here. A is a complex number. This is something we've done before, okay? If for each epsilon greater than 0, there exists, I'll call it a natural number, yes. Let's call it big N, such that for all little n bigger than or equal to big N, the complex norm of A sub n minus A will be less than epsilon. So we can force the terms of the sequence after some point to be arbitrarily close to A. Same for it to be convergent. Okay. as another definition, okay, given a sequence A sub n, I'll write down infinite, because that's what we're going to be talking about, series of A sub n is, well, it's noted with this sum, as I runs from 1 to, well, maybe we'll say n. N runs from 1 to infinity of A sub n, which equals to A sub 1 plus A sub 2 plus forever. Now, given a series, sum, maybe we'll write it as k runs from 1 to infinity, of A sub k, the sequence of partial sums for the series is, well, we're going to call it S sub n, as n runs from 1 to infinity. Okay? Where, so here's how we define this term, S sub n. It's really the addition, so the sum, as k runs, that's k, running from 1 to n of A sub k. Okay. So as a definition, a series, sum k runs from 1 to infinity of A sub k, converges to a complex number, to a number, S, if the sequence of partial sums converges to S. If the sequence of partial sums does not converge to any of them, then we say that this series the series as k runs from 1 to infinity of A sub k diverges. We'd like to get some kind of criteria that helps us determine convergence. And so we have one due to Cauchy. Okay? So let me write this theorem on the board. And so this is due to Cauchy's. The series is the Cauchy criterion, if you will, for convergence for series. The series, the sum as k runs from 1 to infinity of A sub k, converges if and only if for each f epsilon greater than 0, there exists a natural number, exists an integer, natural number. We call it big N, such that for all n bigger than or equal to m bigger than or equal to big N, the sum as k runs from m unto n of a to k in the complex norm being applied to it is less than epsilon. Remember, we're talking complex numbers. Okay? So we want to prove this, and so I'm going to recall a few things. And the first thing we'll recall is the Cauchy criterion for convergence of sequences. And what it says is, if x of n is a sequence of complex numbers, then x of n converges. If and only if it's Cauchy. Is Cauchy. That was one thing. The idea of Cauchiness, if you remember, Cauchy sequences were sequences that get eventually arbitrarily close together, the terms do. Also, so here's where I'm defining what Cauchy means. So it's a definition. A sequence of complex numbers is said to be Cauchy if for each epsilon greater than 0, there exists an n that's a natural number. Remember, J represents a natural number. Such that for all m and n bigger than or equal to big N, the norm, which is x, the norm of x of n minus x of m, will be less than epsilon. Again, we can force the terms of the sequence, if they're Cauchy, to be arbitrarily close to each other. Okay? That's what we can do. Arbitrarily close to each other by pushing far enough along in the sequence. Okay. Well, I'd like to push through this proof of this theorem here for series. So let's do that, and we'll call it quits for that. So here I want to prove I'll call it the Cauchy criterion for series. And really this is just something that stems from the Cauchy criterion for sequences where we apply it to the sequence of partial sums. But here's the proof. We're going to assume or suppose the series converges. Okay? And so, let epsilon be greater than 0 be given. This is part of the statement. You know, what we're trying to do is, if we're saying, hey, if this series converges, remember the statement. If this series converges, then for each epsilon greater than 0, there exists this natural number such that for all m bigger than or equal to n bigger than or equal to the number we find, that the sum from m to n of the a sub k's in the complex norm will be less than epsilon. So that's what we're trying to show. So we're going to let epsilon be greater than 0 be given. Then, because of the convergence of this series, that means that as the sequence of partial sums, so S of n, converges, and that means that S of n is Cauchy. So there exists an integer, say, I don't know, Q, okay, such that for all n and m bigger than or equal to j, S of n minus S of m in the complex norm is less than epsilon. Okay? So without loss of generality, because the way I've said this statement, let's assume n is bigger than or equal to m. My notation here is a little different than what's in the book, but not by much. They have that m is the bigger of the numbers. So, what we have is that because of the norm acting on the partial sum, so here's S of n, it's k running from 1 to n of 8 sub k, that's what S of n is, minus the S of m is the sum as k runs from 1 to m of a sub k. And I'm assuming n is bigger. This will be equal to, well, if you do this subtraction, you make one sum, and it's really the sum as k runs from m plus 1 to n of a sub k. And that's going to be less than epsilon. So, there exists an integer, it's a natural number. Let's say n equal to q plus 1, such that for all n greater than or equal to m, greater than or equal to q plus 1, that's my n. The sum as k runs from m up to n, and of a sub k, the norm of that is less than epsilon. That proves half the theorem. It was an if and only statement, so we got to do the other direction. Here, suppose for each epsilon greater than 0, there exists an integer n, big N, such that for all n bigger than or equal to m, bigger than or equal to big N, the norm of the sum as k runs from m to n of a sub k is less than epsilon. Okay. So what we'll say is there exists an integer. Okay. We'll call it L, equal to n plus 1, such that for all n bigger than or equal to m, bigger than or equal to n plus 1, the sum as k runs from m plus 1, or k runs from m up to n of a sub k will be less than epsilon. So, for all n and bigger than or equal to m, bigger than or equal to this L, S sub n minus S, and this will be m minus 1. Will be equal to this will be equal to the sum as k runs from 1 to n of a sub k minus the sum as k runs from 1 to n minus 1 of a sub k. That norm, that difference in the norm, will be equal to the norm as k runs from k runs from m to n of a sub k, which will be less than epsilon. So, there exists a natural number, it's an integer, it's a natural number, and it is n, such that for all n and m greater than or equal to n, S of n minus S of m will be less than, in the complex norm, will be less than epsilon, and that concludes the proof after I write down the conclusionary statement. So that means that as k runs from 1 to infinity of a sub k, these are the 6 partial sums, they're less than epsilon, but it's Cauchy, and so they converge. So this means that the series converges. I've proven that the S of n is a sequence of a sequence that is Cauchy. That's what we've done. So that proves the theorem. That's enough for this video lecture. Thank you very much for your time and patience.